pushing 40 now. Everyone, welcome to the weekly energy seminar series. Just a brief announcement before we start today. So the first three, including seminars, including today's, have been on some nuclear-based technologies, either SMR reactors in the first talk, or last week and this week on aspects of fusion engineering. So then next week we're going to pivot and start looking at some other topics. So I would encourage everyone to look at the email with all the listings and make sure to come next week. We'll be pivoting away from nuclear-based technologies to look at some other issues in the energy transition. So with that, it's my pleasure to welcome Remi as our speaker today. Remi is a research scientist at the MIT Plasma Science and Fusion Center. I learned about his work on tritium fuel cycle modeling when I was on sabbatical at MIT about a little bit more than a year ago, and it sounded like really interesting work. And so I thought certainly the tritium fuel cycle and tritium modeling is a critical engineering technology challenge for the development of fusion energy. And so without further ado, I'm pleased to welcome Remi to the floor for today's seminar on the tritium fuel cycle. Remi, go ahead.
Thank you very much, George. Hello, everyone. My name is Remi. Thank you very much for having me today. I'm not fully aware if the audience is au fait with all the fusion basics.
Remi, some of us are fusion aficionados, and then I would say the majority are energy aficionados, but not necessarily fusion aficionados.
Okay, so if at any point there's any question that arises, please don't hesitate to chime in and interrupt me. I'm going to talk about the tritium fuel cycle for fusion power plants. Kind of stepping away from a lot of fusion talks that sometimes focus on plasma physics, and here talk about the next challenge once we tick the fusion gain in a fusion reactor. So fusion. So that's the bit that I didn't include. I didn't include the fusion 101. So I'll do it very briefly before starting. Why tritium? Just because tritium is part of the fuel for fusion reactors. We want to fuse deuterium and tritium, which are both isotopes of hydrogen. Deuterium can be found in seawater fairly it's rather abundant in seawater. I think the abundance is 1/1,000. So every 1,000 hydrogen atom is a deuterium. So that's fairly abundant. The problem with tritium is that tritium is radioactive. It has a half-life of 12 years, which means that you can't find it in its natural state on Earth. It decays into helium. It's a beta emitter. You can't find it on Earth in its natural state. Here I have a graph. I took that from a paper from Richard Pearson, so that's 2018, so that might be slightly outdated. But still, it gives an idea of the order of magnitude. The available tritium reserves as of 2018 is about 34 kilograms. In every year, we produce, on average, 2.5 kilograms. And that's mainly from fission reactor. Fission reactors in Canada, CANDU reactors, they use heavy water, and so therefore they produce tritium as a byproduct. And that's where most of the fusion experiments in the world take that tritium. Now, a fusion power plant will consume, it will burn tritium, and this is the amount of tritium burned for 1 gigawatt thermal fusion reactor in 1 year, 50 kilogram on average. This is a lot, and this is a clear demonstration of the problem that we have in the fusion world, is that we need to be fuel self-sufficient. We need to produce our own tritium because we can't rely on existing reserves, and we can't rely on external production because it's just not enough. So as I said, we fuse deuterium and tritium, and that produces an helium nucleus and a neutron. And the idea to breed tritium is to use lithium, so to have the neutron interact with lithium. So you can interact either with lithium-6 or with lithium-7, and both reactions will create a triton. It will also create some alpha particles, and the Li7 reaction will create an additional neutron, which is useful for breeding even more tritium. So the idea is to somehow collect the neutron from the fusion reaction, have it interact with lithium, extract the tritium from that second reaction, and then re-inject that tritium into the plasma. That's the basic theory. The physics of this has been known for quite a while. The challenge is to get a TBR, so a tritium breeding ratio, greater than 1. This is the ratio of how much tritium you produce with these two reactions on the right, divided by how much tritium you burn in your fusion power plant with the reaction on the left. This ratio obviously needs to be greater than 1 in order to be self-sufficient, but we'll see in a minute that it cannot be just 1. It needs to be slightly higher. The question is, how do we can all understand this, and this has been known for quite a while, but how do we have these phenomenon occurring in practice in an actual fusion power plant? We do this in a component that we call the breeding blanket. So this is a very simplified version of a fusion reactor. You have your hot plasma in the middle here, where the fusion reaction occurs, and the neutron, because it has no charge, it will escape the magnetic field, so it won't remain confined in the plasma. The idea is to catch it with a breeding blanket that will surround the plasma. So behind the first wall, we'll have this breeding blanket, which is a component that contains lithium, and this is where the lithium neutron reaction will occur. And just behind that, there's the magnet, and the magnet is very expensive, it's very fragile. So the breeding blanket will also have the role of shielding these components from the deadly neutrons. This is still oversimplified, and it gets trickier when you have to take into account the fact that the breeding blanket is only one component in the whole fuel cycle. This is a sketch from Samuele Meschini, who's now a professor at Politecnico di Torino in Italy. This is from a paper that we published together a few years ago. And I believe George is the co-author of that paper, if I'm not wrong. In this paper, the breeding blanket is just this component here, the lib, the one that's tagged with the lib. And you see that you have all these other components. So one is here, for example, the tritium extraction system. You need to extract the tritium from that blanket. Then you need to separate when you pump your fuel from the plasma, you need to separate the tritium and the deuterium to then put it back into storage and then the fueling system. And then you also have tritium and deuterium from the plasma that are bombarded in the diverter and on the first wall. So you need to process that. So this is a much bigger issue. And all the blue components, all the blue boxes that you see here, we've never integrated that in a fusion reactor yet. The gray boxes, we have some experience with it, with JET, with CMOD. Actually, CMOD didn't run with tritium, but all the tokamaks in the world that were using tritium as fuel had these gray boxes, but the blue boxes, we just have very little experience with it. So this is just a slide I'm going to focus today on the breeding blanket part, but I could go for a full seminar on each of these boxes. This is just to give you an idea of the magnitude of the issue that we haven't had. I'm going to talk a little bit about fuel cycle analysis because this is the tool that we use to design the overall fuel cycle and give requirements on what is the performance that we need to have on each component. So the basic idea of what we call the residence time model is to say that each box will be modeled by, each component will be modeled by a 0D box that has a residence time, tau, an inventory, I, and potentially a source term, S. And there's some inputs and there's some outputs. I'm gonna skip all the notations. Um, but the idea with this kind of modeling is to say that the evolution of the inventory in this box is equal to the sum of all the inputs minus the losses, including the radioactive decay and potentially a source term. If you do that for all the components in the fuel cycle, for example this fuel cycle that I mentioned, you can end up with a system of ODEs that you need to solve. And this model was very well presented in the a paper from Abdu in 2015. And this is the same sort of modeling that we use with Moschini a couple of years ago to get some insight in the for some of the future fusion power plants. We can play with a very simple fuel cycle model just to kind of explain the main problems that we have. So let's make this fuel cycle. So we have a box that is the plasma. That box will burn tritium. Then we have a breeding blanket. There's no actual link between the two. That's why I have a dashed arrow here. But there's you could see it as an input of neutrons. This component obviously breeds tritium with a certain TBR. Then this breeding blanket outputs its inventory to the tritium extraction system that has a different residence time for tritium. And then finally into the storage, the storage and delivery system that then refuels that the tritium into the plasma. So I've done this little animation to kind of so I've basically solved this simple problem and made this little interactive animation to kind of understand how different parameters will work. And here I've focused on the TBR. So what we see here, I've tried to keep the same colors. The blue area is the inventory in the blue box in the storage box. The red area is the inventory in the plasma. The green area is that of the breeder, and then we have the tritium extraction system in purple. What we see when we turn on the reactor, we press the start button of the reactor. I assume it'll work like that one day. We see that first the inventory of the storage decreases. This is because when a triton is bred in the breeding blanket, it takes some time for it to travel the fuel cycle and finally be reinjected in the plasma. There's no way around it. You have to live with this. It can be short, it can be long, but it will exist. During that time, you have to be able to fuel tritium into the plasma, otherwise your reaction will just stop. And if your reaction just stops, then you store your reactor and you have to start over. This is why you start with an initial inventory that we call the startup inventory. Here, I've just took arbitrary units, but here we start with an inventory of 1. It decreases, and then we have an inflection point after 2.5 time units, after which it starts increasing again. And then we have, after when we reach steady state, or pseudo-steady state in that case, we have a steady slope, and we start breeding more tritium. If we increase the TBR, we don't change the time at which the inflection point happens, but we change obviously the final slope of the system. If we decrease it too much, then you see the minimum value of the storage also decreases up until a point where it reaches 0. And if it reaches 0, you just don't have any reaction anymore. If you don't have any reaction anymore, you don't have any neutrons to breed tritium. So you stop your tritium production, and everything stops. So this is what we use to this kind of modeling is what we use to determine the requirements in terms of what is the performance that we need to reach in our breeding blanket for the reactor to be not just self-sufficient, but just to operate on a certain time. In this example with this configuration, the minimum TBR requirement would be something around 1.08. But then you see that I have highlighted here a dashed line, which is 2 times the startup inventory. The reason I've highlighted this specific inventory is because this is the point at which we have created 2 times what we had initially. So, for example, if we have a TBR of 1.17, then this time is reached after 14 time units. 14 times units in that case will be what we call the doubling time. It's the time after which we have created enough tritium in the storage to basically take half of it and start a new reactor, a new identical reactor, and start another one. This is a concept that's very important to understand because having one fusion power plant on the grid is good, but eventually what we want is to have a fleet and to deploy many reactors. And so if this doubling time is too long, and assuming that we are limited by tritium, obviously, if this doubling time is too long, then fusion will never be economically viable because we simply won't be able to deploy enough reactors on the grid to make a significant impact. I believe in the energy market, typical doubling times for power plants are between 2 and 3 years. So that means that if we want fusion to be relevant, we need to hit that target. We need to be able to design a fuel cycle that has a doubling time of 2 to 3 years. So we have three notions. We have the startup inventory. We can't arbitrarily increase it because it is also constrained by safety because tritium is radioactive, so you don't want to have a very large inventory in your power plant. We have the doubling time. This one is driven by economics, as I just mentioned. And finally, we have the TBR. This one, unfortunately, is constrained by technology. The physics is what I already mentioned. The technology is what will drive the TBR. And all these quantities are basically constrained, linked to each other and coupled. If you fix your doubling time, say I want it to be 2 years, this will give you the requirement on the startup inventory that you want to minimize and the TBR that you require to reach this target. If you cap your TBR because this is the max of what you can achieve in the technology, then that means you will have to make decisions on you won't be able to basically choose your doubling time or your startup inventory. This will be governed by the TBR that you have. I've put the link here towards this interactive plot if you want to use it for classes or if you just want to play with it. So this is basically what we've done with Miskini, obviously just on a more complex fuel cycle and not only four boxes. But we've done this analysis for the ARC design. So the ARC design is the design that's currently being pursued by CFS. And the STEP design, so the STEP design is the fusion power plant design for the British program. And we've done the analysis for both these reactors. And just to give you an idea of the magnitude of tritium we will require at startup for ARC, we're talking about maybe a kilogram if we want to account for a reserve, because obviously we could say the minimum TBR is this, but then we want to factor in some safety factor. So the startup inventory will be something higher. So this is why here you have 2 bars for each reactor. For ARC, it will be roughly one kilogram. For another reactor, again, the physics don't change, just a change in technology and design. It shots up to 7 kilograms for STEP. And this is assuming constraining the doubling time to 1 and 2 years, to between 1 and 2 years. What we can do with this analysis is also varying a lot of different parameters, and see the effect that this has on the required TBR. So for example, we changed the residence time. This is the parameter on the top. I actually can't remember all these symbols. I believe BZ is the tau BZ is the residence time in the breeding blanket in the breeding zone. AF is the availability factor of the reactor because obviously a tokamak is pulsed and then you have maintenance, so you have a certain availability factor. But the 2 most important parameters in this study are the TBE and the doubling time. So the doubling time is TD, and the TBE is the tritium burn efficiency. I'm not a plasma physicist, but it is a metric of how efficient you are at burning your fuel. And these are the 2 we saw from that study that these 2 parameters have had the most impact on the TBR that we require. So this is varying the TBE, so in percent, and seeing the effect on the required TBR for 3 doubling times, a doubling time of 1 year, a doubling time of 2 years, and a doubling time of 5 years. So let's just have a look at the orange curve for now. Right now, this is where we are with the state-of-the-art technology for plasma physics. We are around a TBE of 2%. That means that the required TBR is roughly around 1.1. If we can make some plasma improvements, and again, I'm not a plasma physicist, so please don't ask me questions about how we reach that. But if somehow we can increase that number to 10%, then the TBR the required TBR decreases, but still it's between 1.0 and 1.1. So it's still, even with that, we won't be able to drastically reduce it. So the main question here that I'm trying to answer is, how hard is it to achieve a TBR of 1.1? Is it easy? Is it hard? What will it require? So what I propose is that we have a look at the existing concepts for this breeding blanket. There's a couple. They use different types of breeders. They all contain lithium, obviously, but they use different breeders, different coolants. Some are completely disruptive in terms of fundamental design. The first one that I want to talk about is called the water-cooled lithium-lead concept, so WCLL in short. In this concept, it's using liquid lithium lead flowing. So this is this figure here is just a slice of a breeding blanket unit. So you would have dozens of these slices stacked together. This would make one module, and one module here would be a small rectangle, and then you have several modules. None of them is unique. They all none of them is the same. They're all sort of unique. And you would stack them like this and surround your plasma with it. And in this design, in here, we just look at a slice. We have liquid lithium lead flowing from bottom to top. And as it reaches the plasma will be on the left-hand side here. And as it approaches the plasma, it would interact more and more with the neutrons from the plasma, create tritium, and then the idea is to recirculate it towards the back of the breeding blanket. Then there's a manifold, and then this outputs to the tritium extraction system. This has a TBR. This design is assumed to have a TBR of 1.14. So I'll stack all the different TBRs here on a bar plot. Just a segue on our work with James Dark, who published that in 2021. We did a tritium transport simulation of this exact concept a few years ago, using a code called FESTIM that some of you may be aware of. It's an open source code for tritium transport simulation components. So we used the TBR that was taken from the neutronics calculations, and then we just had an advection term. So we have the lithium lead flowing from bottom to top here. And then what we see is that at steady state, so this is a steady state tritium concentration, we have some recirculations occurring because of the cooling pipes. And then that creates a buildup of tritium. This is a problem for several reasons. One, you will have tritium permeating to the cooling channels. That's not something we want. What you would want is to have it recirculate all the way back to the manifold. And that also means that the tritium that's stuck here, in a way, will slow down your fuel cycle. It will take longer for the tritium that's created here to basically be reinjected in the plasma. That means that your fuel cycle is less efficient. That means for a given TBR, your doubling time will be longer. That's a problem. This kind of analysis, for some reason, is not included in the work of the designers for this concept. And it was funny to see that despite knowing this since 2021, when I saw the latest design at the conference last year, I realized that they just made this problem worse by just adding more pipes in this design. So that was made me laugh when I see that. But we'll see how this goes. But there's a lot of work on this design in terms of thermal hydraulics and mechanical analysis, but for some reason not tritium transport. Okay, another concept is the dual-cooled lithium lead. So this concept is similar in the way that it still uses lithium lead as a breeder. It's also liquid, but this time instead of being cooled with water, it's being cooled with water and helium. So I won't talk too much in details about this concept. All I'll say is that this has a TBR allegedly slightly lower, 1.041. And this is the sort of geometry that this analysis is made of, and you can see it's very simplified. But overall, this is the TBR that they obtained, 1.041. Next, we have the helium-cooled pebble bed. So it's sort of self-explanatory. It's cooled with helium only. And instead of having lithium lead this time, we have a ceramics pebble bed. They contain lithium, and so it's a solid. And the idea is to purge it with a gas, heat it up and purge it with a gas. But basically, it's not a flowing system. The pebbles will remain in the blanket unit directly. And this one has apparently a much higher TBR, 1.2. So the HCPB has a TBR of 1.2. Now, the last concept that I want to talk about is the liquid immersion blanket for arc. So in this concept is quite interesting. Instead of having what we call a segmented blanket, where you have these rigid segment modules that are arranged in segments, here the idea is to have your vacuum vessel around your plasma, so the white component here, that will be the first component that the plasma sees, and outside of this component you would have a bath of molten salt. So the arc concept proposes to use molten salt, but basically the concept of the liquid immersion blanket could apply to any liquid, basically. And there's numerous reasons why this concept is attractive. One is that because it's a liquid, it can be pumped, so you can completely empty this reservoir, and that makes the maintenance much easier, and also the replacement. The second is that the blanket, as I said, is outside the vacuum vessel, whereas for the previous concepts, the blanket was inside the vacuum vessel, so it makes the vacuum vessel a lifetime component. That means you cannot replace it over the course of the operation. Was here potentially you can. And it also makes it harder to operate the blanket itself because it has to operate in a vacuum, whereas this operates atmospheric pressure. There's obviously more reasons why this is quite appealing. One of them is neutron shielding. I mentioned that one of the rules of the breeding blanket was to shield from neutrons, and here, because it's a liquid, it doesn't have any damage limit when it's hit by the neutrons, and it doesn't have any gaps, because the problem of having solid segmented blankets is that you always have some gaps, and neutrons, they do love gaps, and so they will find a way through these gaps and eventually come and damage these very expensive magnets that we have here. Enough on the advantages of the liquid immersion blanket. The neutronics analysis, so the calculations that we did for this design, and you can find the reference here, 2022, Gene 1 Bay, 1.05 for TBR. So these are the four concepts. There's more. There are more concepts, obviously. I just picked four because I could have gone on and on for quite a while. But there's something in common with all these concepts, and I'll tell you what in a minute. If we have a look at the three concepts on the left, who are they are candidates for EU demo. If we look at the EU demo requirements, they say that the requirement, and again they obtained this requirement from fuel cycle analysis. The requirement is 1.05 for TBR, for tritium breeding ratio. Now they say, okay, we need to take in some safety factor. So they added a safety factor of 9.5%. So we put the design target just above 1.14, so above here. So here we see that, okay, if we take that into account, according to this graph, only one makes the cut, the HCPB, because it's above the design target, taking into account the safety factor. The big question is, how much do we trust these numerical results? All these TBRs that I show here on this graph, they haven't been measured. They haven't been tested experimentally. It comes from neutronics analysis, so calculation. Basically, we simulate a bunch of neutrons in all directions. It's Monte Carlo, and at some point it says, okay, from this model, this is how much tritium we should in theory produce. And the question that I want to ask everyone is, how much do we trust these results? What's the error bar on these values? The main problem in our I see a message in the chat. Okay, so sorry if I missed that. Sergey is asking why is the Ark's TBR so low? I must admit I don't know. All I know is that the overall volume of the blanket is smaller than for other reactors. That's also one of the key features of the Arc reactor. I must admit I haven't read all the papers in detail. It's also using a different breeder. It's using FLIBE, a molten salt. Um, there's probably a lot more neutron multiplicator in these other designs. I would have to dig it up. The reason why I didn't put the bar all the way there is because demo and arc are so different. They don't have the same requirements. So that doesn't mean that this TBR wouldn't make the cut in terms of tritium self-sufficiency. I didn't have time to find the requirement for arc. Question from Michael is it natural lithium or enriched lithium-6? This is still a topic of debate. I have a slide somewhere about the different isotopes. The reason why you would like to enrich with lithium-6 is because there's a higher probability of the tritium production reaction. However, lithium enrichment at large scale is still a technology that needs to be developed. It's still a debate whether you need to enrich, and if you have to enrich, what percentage you need to enrich. I believe in the arc calculations, these, and actually in all the reactions, this might be with enriched lithium-6. It's a good question though. I should double check. If you have questions, do you mind raising your hand or just turning on your mic, because I may miss some questions in the chat.
Sure, I'll also try to keep an eye on the chat.
Okay, thanks so much. So the problem that we have right now in our community is that the current reactors, none of them breed tritium. Some of them burn tritium. There's a case for JET. It will be the case for ITER. It will be the case for Spark, but none of them breeds tritium. None of them is designed to be tritium self-sufficient. There is a program in ITER called the tritium breeding system, where we try to plug in some mockups, and I'll come to that in a minute. But none of them breed tritium. And we are in a bit of a catch-22 situation, like often in fusion, was the fusion power plants will allow us to test the breeding blanket design. But we need the breeding blanket design to build a fusion power plant, because if there is one component that you can't allow to mess up in a fusion power plant, is the tritium breeding blanket. Just because if it's not as performant as you thought, your reactor simply won't work. It's not just a matter of it will work with less efficiency or it will be less powerful. It will simply won't not work. And that's what I showed with the simple fuel cycle analysis. If for some reason at some point you don't breed enough tritium, everything will just stop. That's a big issue. If we look at the EU demo plan, for testing these breeding blanket technology, the first step is to build ITER. Now I put here pause for dramatic effect. ITER is very large. It has its delays. It has its challenges. It will take a very long time to build it. Then at some point, the idea is to plug, as I said, some mock-ups. And I believe now with the new baseline, we want to test only two candidates in ITER. So maybe this figure is slightly outdated. The next step is to pick the best one, not necessarily the one that worked, but just the best one out of the two. And then for the first time, build a full-scale prototype for demo. And then I guess there's another step, which is build demo. I should pause as well for dramatic effect. And then the final step is just cross your fingers and hope that everything scales well. And the plan B is, well, simply there's no plan B. If any of these steps doesn't work, then I don't know what we would do. What we propose at MIT is to try and see if there's an alternative route. And this is the LIBRA project I want to talk about now. So the idea is to say, let's not wait for ARC to see if it works or if it doesn't work, the concept of the liquid immersion blanket. The question that we ask ourselves in that team is what is the smallest breeding blanket we could build to demonstrate a TBR of 1? And this is the experiment, the concept that we came with. This is the LIBRA experiment. I'll go into details in a minute, but you see that we think we can test this technology in a lab scale experiment. It's not a small experiment. But it's much smaller than waiting to build a arc reactor to see if it works or if it doesn't work. So we have three main objectives. The first one is to demonstrate tritium self-sufficiency with DT neutrons. We would like to measure a TBR as close as possible to 1, if not greater than 1. We want to use this experiment, which is a first of a kind experiment, to validate neutronics models and tritium transport models. So I showed earlier some tritium transport modeling with FESTIM, but obviously none of it is validated yet at this scale, at least at the component scale, because we've never built a component like this. And the third objective is to investigate tritium extraction from these liquid breeders, because it's all well and good to breed enough tritium, but if you're not able to extract it, it's as good as having a TBR of 0. So this is also something that we want to test with LIBRA. I'll go into a bit more details about the LIBRA experiment itself. So what we want to do is basically have a tank of molten salt, so FLIBE. So we think we need about 500 liters, and have a neutron source, which is a DT neutron source. So why we want a DT neutron source? So it's because we want to have the right neutrons, because not all neutrons are equal, and especially when it comes to tritium breeding, you want to have the right energy spectrum, because as I alluded towards you a bit earlier, you have different probability of creating tritium depending on the energy of the incoming neutron. So it's very important to have the right neutron so that you can extrapolate better into a fusion power plant. The neutron generator will obviously produce a lot of neutrons in every direction. The idea is to have a full pi coverage of the neutron source so that all the neutrons are captured by the lithium in the salt and then creating tritium. Then we have a neutron multiplier around it, and we have a double inconel wall to collect all the tritium. So this is what happens after the tritium is produced from the neutron reactions. It will be transported in the salt either via diffusion, just because tritium is small, it can diffuse. That happens in metals, for instance. But because here we have a liquid, it will be advected and carried away by the flow of the salt itself. Then there's two pathways are possible in this configuration. One is simply being released into the gas phase, so that headspace here is a gas phase, and so it can be outgassed directly into that phase, or it can also permeate that that inner wall, and then be released in this middle space here. So we have these two pathways for tritium release, and the way we collect them, we collect the tritium is to have a gas. So in that case, we're using helium. We have helium flowing into that middle space, for instance, and then we collect it all the way. We carry it all the way to our tritium detection system. And for the blue pathway that I show here, it's the exact same thing. We just have a second gas stream. To go to TBR of 1, I mentioned earlier, we need about 500 liters of salt. It's a big experiment. So we thought we could start smaller and build a smaller experiment that won't have a TBR of 1, but still we can use that to commission the subsystems, so the tritium detection systems, the neutron generator, and we can use that experiment to slowly build up experience and build up expertise in this kind of experiment. So this is called the BABY program. So we started with a very small capsule, about 100 milliliters of salt, and this is what you see here. And we had a TBR of roughly 10 to the minus 4. Then we moved to BABY 1 liter. We're doing this upgrade right now, and this will have about an order of magnitude higher TBR. Then finally to LIBRA Pi. The reason we call it Pi is because it's a pi coverage. And if LIBRA Pi is successful, then we just build 3 more of these quadrants, and we can build a full-scale LIBRA, and that should hopefully, according to the modeling, get us to TBR of 1. I see a question in the chat. Any particular why we're using helium? No, apart the fact that it's an inert gas, no. We plan to add a little bit of H2 in this gas stream just to see if it helps via isotopic exchange, if it helps removing the tritium faster. But we could have used argon, for instance. Okay, so in this experiment, we want to measure a TBR. It's all well and good to model it, but we want to measure it. Not all. We want to measure it. So remember the TBR, the tritium breeding ratio, is the ratio of how much tritium we produce divided by how much tritium we consume. In our case, in our configuration, this is equivalent to how much tritium we produce divided by how much neutrons we have produced in our DT generator, because every 14 MeV neutron comes from a DT reaction. So every neutron comes from burning one triton in our generator. So if we want to measure TBR, all we have to do is to measure these two numbers with as much accuracy as we can. This is a presentation of the baby 100 milliliter experiment. This experiment is not running anymore because we upgraded it. But what you see, the few elements that you see is you have the brownish bit here is the crucible with the salt in it. So it's wrapped up in a lot of insulation. You have two neutron generators around it, so on both sides. So it's being bombarded with neutrons all the time. We have a few elements for the gas handling and so the gas bottles on the left here, and this on this rack you have a this is our tritium collection system, and we're using liquid scintillation for collecting. I'll come back to that in a minute. We obviously modeled it with neutronics. So a few words on neutronics and what this is. This is simply simulating the path of neutrons based on their interaction with materials around them. So the neutrons are born in the two neutron generators on left and right here, and then they will be shot in every direction. Some of them will interact with the molten salt in blue. The bit that you see in the middle is a heater. So we have a heater that's immersed in the salt, and that gets it up to 700 C to keep it molten. So some of these neutrons will interact with the salt, producing tritium, and you know the rest. So we have some ideas of the TBR that we should obtain. We did the calculation with different breeders. One with FLIBE, one with a surrogate salt that we call Cliff, one with FlyNac, it's another molten salt, and one with lithium lead. And interestingly enough, at this scale, at the 100 milliliter scale, the breeder that gives the highest TBR is this surrogate salt and not FLIBE, and not lithium lead. This may seem a bit counterintuitive because FLIBE has barium in it, which acts as a neutron multiplier. Same for lead in LIPB. But the reason why the Cliff has the highest TBR is because there's not enough salt to moderate the neutrons, and therefore, if they can't be moderated, that means that they don't lose energy. And if they don't lose energy, they remain in this right-hand side of this plot. This plot is basically the probability of the two tritium production reaction occurring. I apologize, the colors are switched. It's the Li6 reaction is in blue on the graph, and the Li6 is in orange on the bar plot. But what we show on the bar plot is the contribution of each isotope to the global TBR. And we see that it's dominated by the lithium-7 reaction. So this bit on the end here. Obviously, if we move to a bigger volume of salt, then neutrons will start decelerating and losing some of their energy. So moving towards the left on that graph. And so obviously you would start kicking in the lithium-6 reaction, which is why you would like to enrich it. Same goes for barium multiplication and lead multiplication. To detect neutrons in this experiment, we use an array of techniques, but the most robust technique that we found is using activation foils. So these are tiny pieces in that case, niobium, that we place on the top of the neutron generator, and these foils will basically activate. So the niobium that's in this piece of metal, it will activate, and as it decays, we'll be basically able to count this decay, and that will give us an information about the total neutron fluence that this piece of metal saw. Then we use diamond detectors. Diamond detectors are a bit trickier to calibrate. So the graph that I show here is not calibrated, it's just a count rate of the detector. But if we look at the N alpha peak of this detector, we can have the real-time data um, of the experiment. So in this experiment, we turn on the reactor at time 0. We can see that it's not super steady. We don't really know what happened here, but we can average things out for analysis. Then we keep it running for 12 hours. Then we go back to sleep because we don't want to organize night shifts for this experiment. We come back the next morning, we turn it up again, and we irradiate for another 12 hours. So the combination of both techniques can give us a fairly accurate measurement of the neutron fluence and the neutron rate if we combine it with the diamond detector. For tritium collection, we use we use something called liquid scintillation counting. So the basic idea is to have the gas stream pass through several volumes of water, and this will allow us to strip all the soluble forms of tritium from the gas stream. So we have two valves first, and that will strip out all the soluble forms, so HTO, so tritiated water, TF, and TCl. But some forms are not soluble. So that's the case for HT and T2, for instance. This is not soluble in water. So if we want to also collect that, we need to have this gas stream pass through an oxidation furnace that will convert everything into HTO, so tritiated water, which is soluble, it's water, and then pass it into another set of two valves. Then what we do with this water that collected all the tritium is that we put it in a liquid scintillation counter. So we mix it with a scintillation cocktail, and the decay of the tritium that emits an electron will basically activate some molecules in this cocktail that will emit a flash of light. Then the principle is simply to count these flashes of light over a certain period of time, and that gives us an information about the activity, the tritium activity, radioactivity of the water. Okay, so enough about the method. What we want is to have the actual results. So for this experiment, we measured a TBR of we measured a production of about 10 to the 10 tritons, and we produced 10 to the 13 neutrons, which gives us a TBR of 3.57 10 to the minus 4. That means that roughly for every 10,000 neutrons, we produced one tritium atom. It's very small, and you won't build a fusion reactor out of this, but it was kind of expected based on the modeling that we did with OpenMC. The goal of this experiment was not to get a high TBR, it was to start commissioning the system. But however small this TBR was, it was the world record for measured TBR simply because it hasn't been done by anyone else. So this was the state of the art and the highest TBR we ever measured experimentally. This has no modeling factored in whatsoever. It's a purely experimental measurement of a TBR of a breeding blanket, and it's very small. Just gives us an idea of the way the path that needs to be done to get to an actual component for a breeding blanket. But we still have this small discrepancy about 20%. We didn't measure. We seem to have produced less tritium that we expected, and our hypothesis is that tritium was lost to permeation. If you look at the design of this initial experiment, it doesn't have an outer vessel, so we were not collecting the tritium that permeated out of the crucible. It was a design choice. Again, it was because this experiment was meant to just commission the subsystems and not necessarily have a very robust accountancy of the tritium. So keep that in mind. 10 to the minus 4 measured TBR. This was done in it was just published in Nuclear Fusion, but this experiment was done actually last year. Um, and it was at the time the world record. How we can use this data is to calibrate a simple model. It's a 0D model. We can use that to infer some physical parameters of this setup. So it's a very simple model. It says that the evolution of the tritium inventory. So C here is the tritium concentration in the salt. The evolution of the tritium inventory is equal to the source minus the losses. It's dead simple. We express the source as the TBR times the neutron flux, and we express the losses as the product of the surface area of the pathway. So in that case, the wall surface area, for instance, times the a factor k that we call the mass transport coefficient, and this is an unknown, and the times the is proportional to the salt concentration of tritium. If we plug in this model and we solve it, and we plug in the TBR that was expected from OpenMC, the neutron rate that we measured, and we let the mass transport coefficient to be 3 parameters, we can get a fairly good agreement with the measurement. So what we see on this graph is the x-axis is the time of the experiment. So the experiment lasted 7 days. And the y-axis is the cumulative release. So it's expressed in becquerel just because it's easier to express small quantities of tritium in becquerel. And it shows how the cumulative release evolved as a function of time. The red bands here are the 12-hour radiation, the two 12-hour radiations that we had for this experiment. And we can fit the measurements in dots fairly well. Obviously, we don't have dots for the green curve, which is the wall release, just because, as I said, we don't have an outer vessel for this experiment. But we had a good agreement. We can use this fairly simple model to play with the parameters and see what happens if, for example, here we vary the mass transport coefficient plus or minus 30%. And we see that we start seeing some uncertainty, but the final value doesn't change. It just changes the rate at which the tritium is released. That's very good because if we want to measure TBR, we basically don't care about the dynamics. If we just want to measure TBR, what matters is this final point when all the tritium is being released from the experiment. What we did with this experiment at the CID scale is that first we repeated it. So you see all the gray curves are this first one was at the very initial stages of the experiment, and we weren't controlling the experiment that well. But we repeated that experiment several times with pure molten salt. And then we had the idea of adding europium fluoride, so EUF3, 4%, to change the redox potential, so how corrosive the salt was. So we wanted to make our salts more corrosive and see what would happen. So we saw that it affected the release rate. All of a sudden, we would release less, the tritium would be released at a much slower rate. So that experiment lasted 14 days instead of 7. The second change that we see is also that overall we released less tritium. We obviously had the same TBR because the geometry hasn't changed. There's still the same amount of lithium in the salt, but for some reason less was released at that top surface, and we still don't really know why. Remember the safety factor of 9.5%. This is way more than 9.5%. And this was just adding 4% of europium fluoride in our setup. The other change that we saw was the speciation of tritium. So what chemical forms tritium had in our experiment. In the pure cliff experiment, we produced about 21 becquerel of HT, and it was only HT. But in this experiment, we produced a mix of, it was not a one-to-one switch, but we produced a mix of HTO, TF, TCl, and HT. And we associate that with simply the effect of the redox potential on the different chemical reactions that occur. as I said, we upgraded that setup to the baby 1 liter experiment. The first upgrade is the new crucible. So we'll still have a molten salt, but this time it's the same salt, but this time we have 10 times the salt volume, so 1 liter. We added an outer vessel to be able to collect the tritium that permeates out, and we still have the headspace where we sweep some gas to collect the tritium that was released in this gas phase. Because we have a higher TBR, we can afford to only have one neutron generator, simply because that means we don't have to produce more neutrons to be able to detect tritium. We can afford to just have one, so it simplifies things a bit. And this time we're using two bubblers because we have two streams. So we want to have two bubblers to collect both gas streams. And this is what we obtained. So this was an experiment that we ran, I believe, in the autumn, if I'm not mistaken. And it's still being analyzed. The data is still being analyzed, but the TBR that we measured was 2.26 10 to the minus 3. So that's a times 6 improvement compared to the previous experiment. Again, this was sort of expected. The red bars here are the computed TBR with OpenMC with neutronics, and you see that we have a fairly good agreement, plus or minus these 20% that we have here, and I believe this a bit less than 20%, but still we have a certain discrepancy. What's tricky here is to quantify the error bars to be able to do some uncertainty quantification. This is somehow doable for the experiment, but a bit trickier to do for the OpenMC because of course OpenMC is Monte Carlo, so you could compute your statistical error, but that doesn't tell you a lot about the true error of the model, which is what you forgot to put in. What have you omitted? But yeah, this is the new world record. 10 to the minus 3. This is the state of the art of the tritium breeding ratio in the fusion community. Now all we need to do is time this by 500, and we'll have a breeding blanket that produces more tritium. We ran the same tritium release analysis, and these are the results for the cumulative tritium release of the dynamics. The experiment took much longer to run. It took 44 days. It took 34 days to run, and when we look at this, even though the points are on the, obviously we have some free parameters, so it's easy to fit it, but we when we saw that first, we raised a few eyebrows because we had a few buts. One is the 0D assumption still valid in this case? We know that the tritium production is not homogeneous, so the source term is not homogeneous in this volume, and we know that the temperature is not homogeneous anymore. Just because we have a bigger volume, we have more heat losses, and so we know we have a hard time heating it to an homogeneous temperature. Then the big question is, why do we not have permeation? Um, these are false positives. It looks like we have a teeny tiny bit of permeation, but these should be almost zeros actually. And even if they weren't, we expected about 20% permeation. We're far from having 20% of permeated tritium. So that's a big question that we still have to answer. We have a few ideas, but we still have to answer it. And finally, we want to reproduce it. This was the very first experiment done with baby 1 liter. We want to reproduce it. This is, as a backup slide, this is the current experiment that's running right now. I think right now we have a few more data points that we could add, but we are currently reproducing that experiment. Okay, so where do we want to go from here? We measured a teeny tiny TBR, even though it's a world record, as I like to say. It's still small. We want to scale up. So where will we go from here? So first, we want to use these experiments are, yes, they're meant to commission the subsystems and help us gain experience on tritium breeding technologies and salt handling and all that. But we'll also use it to already validate the models. So I talked about FESTIM. It's an open source code for tritium transport. I put all the link here to the GitHub repository. We're already using FESTIM to simulate this experiment. So here's a temperature field, so the temperature distribution in the molten salt, and simulating a gradient of temperature, and that drives some advection, some convection in the salt, and from that we can solve the tritium diffusion equations and obtain the final the evolution of the tritium concentration field in the salt. And then from this, um, we can we can compute the surface fluxes. So, for example, the wall release, so everything that's released that's permeating through the walls, and everything that's being released on the top surface. And already we see that there's a big. When we ran this for the first time, I had a student, Colin Weaver, who was doing this FESTIM modeling for me, and he did a great job. But we saw this discrepancy where we expected to have 20% of wall release, and we ended up with having the release being dominated by the permeation. So that's a big discrepancy. What we also saw is that even though this has nothing to do with TBR, because TBR is obtained with neutronics calculations, all measured, um, but it's very sensitive to the tritium diffusivity in the salt. We have some inherent uncertainty in the literature when you look at the diffusivity and solubility of tritium in molten salts. That's the case also for lithium lead, by the way. And this is what the band is. If tritium is very mobile in the salt, then you would have the top line here. If it's more on the low end of the diffusivity, then you would have the lower curve. So it's quite a band already. Then we have this massive discrepancy that I talked about. We have a few hypotheses for why this is happening. One is that maybe in our model we didn't take advection correctly into account in this model. We're starting to think about the formation of potentially a permeation barrier on the surface of the crucible, so maybe like an oxide layer or something. And then we already know that the chemistry in these systems is fairly complex, and so this will need to be taken into account more seriously into this sort of modeling. So we have ideas. So this is where we're heading in that regard. Then the big question is, our neutronics model, is it an accurate representation of the actual experiment? This is, for the 1 liter experiment, this is the OpenMC geometry. And so you have the main elements. You have the molten salt in yellow here. You have the reddish here is helium. You have the Inconel in blue. You have the table on which it's sitting, the epoxy plate, the neutron source. You have the support here. These orange bricks are lead bricks, but this is the actual setup. And so the big question is this an accurate representation? Beyond the statistical error inherent to Monte Carlo, is what are we forgetting things on this model? And are we forgetting things that are very important? For instance, these 4 lead bricks, when we first modeled the experiment, we forgot to account for these 4 lead bricks, which are there for support, just for support. They weren't put here thinking we will use that to multiply neutrons or anything. But when we added the 4 lead bricks into the model, we had a boost in the expected TBR of 11%. Remember the safety factor of 9.5%. This is just forgetting that we had 4 lead bricks hanging around for supporting the neutron source. Then this baby experiment is already informing the design of future experiment. This is the whole point of having the stage approach. So LIBRA is a scale up to 100 liters of salt. The main part is already manufactured, but we are now waiting for data to see what we do regarding the permeation. This is the inner vessel, and it's still waiting to have the outer vessel added to it. And the reason why we put things on pause is because we want to wait and learn from the baby 1 liter and learn about the dynamics of permeation. Is permeation an issue? Do we even have permeation in this experiment? We can't measure it, but does that mean that we are messing something with the detection system, or does that mean that simply permeation doesn't occur at all? We're waiting on that to inform the next stage of the manufacture of this experiment. Okay, I hope I'm on time. I'm very sorry if I spoke for too long, but a few takeaways. If there's only a few bits to remember from that seminar, um, it would be that tritium self-sufficiency is the next big risk item on the fusion roadmap. I'm not a plasma physicist. I'm fairly confident that we will tick the Q plasma box sooner or later. I think we'll be fairly close. But the next big thing will be, okay, you can get a fusion gain, but do you actually have the fuel to fuel your reactor? Having a plasma gain of 40 is completely useless if you don't have the fuel to fuel this Q plasma. We have a safety factor on TBR of 9.5, but maybe the real uncertainty is much larger. Up to now, the R&D was mostly, I put only in brackets because I can't say for sure, but it looks like when you read the literature, it's mostly focused on computational studies, and you need them. You need them for sure. I come from the computational background, so I do love a model, but you also need to have some experiment to make sure that you haven't forgotten anything. This may look a bit bleak, but there are a few initiatives that personally give me hope. We talked about LIBRA, obviously. Recently, you may have heard of the Liberty Project, which is a UK-led program for developing tritium breeding technologies, which could be seen as a scale-up of LIBRA using a much higher neutron source. We'll see what this goes, but I'm fairly supportive of this program. And we have in Europe the VNS program. So the VNS stands for volumetric neutron source. It's a small tokamak. The concept is how to have a small tokamak as part of the Eurofusion framework dedicated to testing breeding blanket components. So it's still under discussions. It's not confirmed yet. I don't know if it's funded yet. But there is this paper that I think you guys could read if you want to have more details about this. But the main questions that I want to leave out there for maybe future discussion is: will all of this be enough, and will all of this be soon enough to build a first of a kind fusion power plant by the 30s, 40s? Some private companies have very aggressive timelines for demonstration power plants, and I'm putting this question to this group: is do we think that this will be enough, and do we think that we are going fast enough to solve these issues? With that, I thank you very much for your attention. If you have any questions, please do not hesitate. I put my email here. Feel free to reach out to me if you have any more questions. I'm always happy to chat and discuss about all this. Thank you very much.
Thanks, Remi. We'll take time for a few questions. Sergey, looked like you had your hand up first. Go ahead.
If you would enrich your lithium component with lithium-6, what are your expectation? How much you will be increased breeding ratio?
It's a good
How much? And this
it's
is
a
the
good
first.
question.
And if you don't mind, if are you in this transport modeling you were talking about? Are you considering thermal diffusion effects? Because you mentioned about diffusion, but you have very large temperature gradients as well, and there is also thermal diffusion effects. The model accounts for that.
So I'll start with the first question about the enrichment. At this scale, if you look at this bar plot, you see that increasing the lithium-6 wouldn't do much. Increasing the lithium-6 composition would basically blow up a little bit this orange bit. But since we don't have enough, it's just driven by the volume. We don't have enough salt to moderate the neutrons, and because the lithium-6 reaction kicks in for thermal neutrons.
No, Remi, wait a second. You do not have your kind of this experiment is not big enough to moderate neutrons. But
Yes.
if we were talking about big system, then you have plenty. Moreover, you must moderate neutrons.
Yes. So that's why I started by saying with this experiment, at the 100 milliliter scale, enriching the lithium wouldn't do much. Same for the 1 liter scale. It wouldn't do much. I'm not saying it would do nothing, but it wouldn't do much. Obviously, at the larger scale, having enrichment allows you to have a higher TBR. So I don't have the whole calculation here for the TBR of the full scale LIBRA. But if you look at the initial LIBRA paper that Sarah Ferry published in 2022, we have done the OpenMC calculation with or without. Oh, I'm sorry, I don't have it here. I'll send it in the chat when I can. We've done the calculation with or without enrichment, and yes, we do have a change. And I believe it's changed by maybe 20%. But not at the scale that we're working with the baby program. That's what I wanted to say. The second question was, do we
diffusion.
So are you talking here about? I assume you're talking about the Sorey effect.
Yeah, you guys call it Sorey effect. The plasma guys call it thermodiffusion.
It has several names: thermal diffusion, thermophoresis, Sorey effect. So the code itself can account for it. The feature exists in the code. We're not accounted for it yet, simply because we don't know the Sorey coefficient, the heat of transport coefficient. Again, that has several names. There's already a massive discrepancy in, if you just look at the solubility of tritium in molten salts. If you look at the literature, there's orders of magnitude difference depending on the author. So I can only imagine what it would be for the heat of transport, but I'm not aware of any study that measured it. I know that recently some group has started to calculate the Sorey effect with molecular dynamics. I'm not aware of it being done for molten salts yet.
Okay,
But if you know more, please don't hesitate to reach out. I'm interested.
Okay.
All right, any last questions for Remi? We're kind of at time, so.
Very sorry, it's my fault.
No problem. Very, very interesting work and very exciting to see finally some experiments going on this. Be curious to see how the full scale experiment comes out over the next year or so.
I see that Stefano put the link to
there's in the chat, Sergey, there's a link to the question that you asked about the effect of lithium-6 on TBR in a large system. So there's a link there.
Thank you so much, Stefano.
All right. Thank you again, Remi. Very interesting.
Thank you very much.
We appreciate it. And we will see everyone next time at the seminar. Take care.
Thank you all. Bye-bye.
Thank you.